Jai Hind. In today's lecture, we'll talk about statistical learning in artificial intelligence, and we will consider in statistical learning the Bayesian learning. Then what how we can improve the performance by just using the maximum posterior. Then we'll talk about maximum likelihood and MDL, and we'll conclude it with learning with complete data. And during the discussion, we will include an example. So now let me start with the statistical learning. Where do we want statistical learning? When we are having uncertainty in our domain. We can understand the point that in real world, the things are not certain. We plan something, it may happen or may not happen. So there are chances of happening. So when we are having learning as a form of uncertain reasoning from the observation, then we do statistical learning. It means we are having observation. With help of observations, we will do uncertain reasoning. Okay, when we do learning for this type of thing, then that is called statistical learning. When we are talking about uncertainty, so uncertainty can be handled by the probability theory. Agents can handle uncertainty by using the method of probability and decision theory. So for that, they need to learn their probabilistic theories of the world from the experience. Okay, so what we will have, we will experience in the domain, then we will get some evidence, and based on those, we will make the theories. When we say that we take experience, so we are having data. Whatever we do, we record that creates our data, and that data is actually our evidence. What is that? Instantiation of some or all of the random variables describing the domain. The domain is described by some random variables. Okay, when we are having probabilistic theories, means we are having some uncertainty in the domain, then we will be able to find out the probability. That what is the probability of occurring of this particular event. So we will create our instances, and that are our data. When we have our data and we are having the domain, in the domain the things are working. How that domain is working, those are the hypotheses. And these are our probabilistic theory of the domain, the working of the domain. So in statistical learning, we will have evidence and we will have hypothesis. When we are having evidence and hypothesis, based on that we can do learning. And learning for what? For our uncertain reasoning, and we'll do it from the observation. The observations will be used to create the evidence. Okay, so now we are having data, and we are having hypothesis. So how do we learn? So we will learn the different techniques of doing the statistical learning. I'm starting with the first one, that is Bayesian learning. We view learning as Bayesian updating of probability distribution. Bayesian updating means we are using the Bayes theorem. We are having the Bayes theorem for conditional probability that we will use here. View learning as Bayesian updating of a probability distribution over the hypothesis space. We are having different possible hypotheses, and hypotheses are telling us that how the domain is working. So over that hypothesis space, we will have the probability distribution, and what we will use here, that is the Bayes theorem, that is Bayesian updating. H is the hypothesis variable. So what is my hypothesis space? That is having all the possible hypotheses. Let me say H is the hypothesis variable. So what are the possible hypotheses? Those will be the values H1, H2, Nn be the possible hypothesis. I am denoting by H, but it could be H1, H2, Hn, any hypothesis. And how we are defining these hypotheses, how the domain is working. That is according to the working in the domain. Let D is D1, D2, Dn be the observed data vector. We will have some hypothesis that will denote the domain, and we will have our observation. So we are taking that as D. It could be D1, D2, Dn. These are our observation. So I'm taking it as observed data vector. And X we are using to denote the prediction. X the prediction. So what we will do in Bayesian learning, we compute the probability of each hypothesis given the data. What are the hypotheses? For each hypothesis, we will compute the probability. Then X is our prediction. How we will do the prediction? Prediction we will be based on this basis. What basis? For each hypothesis, we are having probability. So how do we make prediction? The predictions are made by using all the hypotheses weighted by their probabilities. So we will calculate the probability of each hypothesis, and the prediction will be based on that hypothesis, and it will be weighted by, means multiplied by the probability of that particular hypothesis. We will not take just the one, just the best one. No, we will take the weighted average of all the hypotheses. So what actually we are having, the Bayesian setting, the learning in Bayesian setting is actually probabilistic inference. Why? Because we are giving the weights according to the probability of that particular hypothesis. So it is probabilistic inference. This is our statistical learning, one way, that is Bayesian learning. So let us once write here the Bayes theorem that we are going to use further. What Bayes theorem says, the probability of A is one event and B is another event. Probability of A when B has happened is equal to probability of B when A has happened into probability of A divided by probability of B. This is our Bayes theorem. So we are going to use it in our Bayes learning. So what we said, it will be weighted by the probability. Okay. So what is the prediction? The probability that prediction is X. We said X is our prediction. So what is the probability that it will be observed? It will be there. Probability of X when D is observed. So this is, let me repeat. What we are having, X is prediction and X will be predicted. What is the probability? So probability of X when D is the observation is sum of, what we said, weighted average. Okay. So it will be sum of the probability of X when data observation is D and hypothesis is HI into probability of that hypothesis, that is the weighted average. The prediction that X is there when hypothesis H1 is weighted by the probability of H1. Same way for H2, H3. So that's why we have taken summation I. We will consider all the hypothesis probabilities and that will be multiplied by. Okay. Now what we are having? When we have probability of HI counted when D is the observation, so we can simply take it as probability of X when HI is there. D is our observation. Based on that, we have calculated HI. Okay. So by the rule, we can write it probability of X when HI is there into probability of HI when D is the observation. And that is what we were going to calculate. So prediction is weighted average over the prediction of individual hypothesis, as we said. This is the prediction based on individual hypothesis, and we have taken the weighted average with the help of their probabilities. Now what these hypotheses are? These hypotheses are playing the role of intermediate. These are intermediaries between the data and the prediction. We have observed data and we have to do prediction. So these hypotheses are playing the intermediate role. These are intermediaries between the data and the prediction. Okay. Now, when we are doing this, the weighted average, we need to compute all the probabilities, probability of all the hypotheses when observation is D. That is the requirement of calculation. So now let us understand the terms. We have talked about Bayesian learning now. So in Bayesian learning, how do we denote these probabilities? So those are the basic terms that are used for here. Probability of HI. Now what we are calculating? We are calculating the probabilities of hypothesis, probability of prediction. So what terms we use for Bayesian learning? PHI. That is probability of hypothesis. We are having different ways of working. So we are having different hypotheses. Okay. So the probability of hypothesis is called the prior probability. Now the question is, how do we calculate the prior probability? And what is use of doing this prior probability? This is calculated from our experience. If we are working in some domain and we are aware when time passes, and with time we find out that this thing is happening in this way occasionally or oftenly or always. So based on that we calculate prior. So this prior probability we will understand with our example. Now probability of HI, when we have this observation. Now there was no condition. That was the prior probability when nothing has happened. How do we calculate probability when nothing has happened? That is with experience. That is prior probability. And when we have observed something, now when we calculate the probability of hypothesis, when we have observed D, that is called posterior probability. So now something has happened. So this is posterior. So probability of hypothesis without any observation is prior, and with after observation it is posterior probability. If we apply the Bayesian rule, then probability of HI when D is there is equal to probability of D when HI is there into probability of HI. We will have denominator also. What is there in what is denominator in Bayes rule? That will be probability of D. Okay, but because observation probability is constant, so we ignore this in calculation because it will have the same effect on all the calculations. Okay, so we will take just this product of probabilities. Now see what we have calculated. What we have calculated? That is probability of HI when D is there. This is posterior. Now in posterior, what we are calculating probability of observation when hypothesis is there. Okay, when hypothesis is given and we are finding the probability of data observation, that is called likelihood. When observation is there, the probability of hypothesis is called posterior. And the probability of observation when hypothesis is given is called likelihood. Okay, and let us denote H map, a specific type of hypothesis. What is that? Let H map be the hypothesis for which the posterior probability is maximal. What is posterior probability? This. The probability of hypothesis when observation is D. This is called maximum a posterior hypothesis. Okay, so on this slide we have just taken a name for a hypothesis which is having the maximum probability. So now let us understand the terms with help of this example. In this example, we are having two flavors of candy, cherry and lime. and these are wrapped in a same opaque wrapper. So because both are wrapped in same opaque, same type of wrapper, so we are not able to see within it is cherry candy or lime candy. And how these are sold? These are sold according to these 5 hypotheses. We are having large bags, and how these large bags are actually packed up, and how these are packed up and distributed. H1 says that in the bag all the candies are cherries. H5 says that all are limes. H2 says that 75% are cherries and 25% are lime. Opposite, 1/4 are cherries and 3/4 are lime. Here 50-50. So this is the way the domain is designed. The domain is working. So the working of the domain has been represented with the help of the hypothesis. Okay. Now, what are the prior probabilities given here? That is 0.1, 2, 4, 0.2, 0.1. This is the prior probability. Now, when we are given prior probability, so this we have come from the experience. Let me say I'm running a store and I'm getting these bags from the manufacturer. Then by experience, I'll come to know that 40% of the bags are generally 50-50 cherries and limes. So how will I come to know that 40% bags are cherries and limes? Because we are taking the packets from the manufacturer for a long time, and that is our observation. That is our experience. That is not current observation. That is our experience. We have observed it throughout 2 years, 3 years. Okay. And very rare means only 10% time we are getting only cherries or only limes. So how this data has been taken? It has been taken from prior. What is use of this prior probability? It controls the complexity of the model. How it is calculated? It is calculated based on the knowledge, what knowledge we are having with experience, and it controls the complexity of the model, because something already we know. That is better than knowing nothing about the domain. Now, what else is? Now, let me say my observation. So, what is this? What is posterior? Posterior is when there is some observation. Okay. So, now see, what is posterior? So, initially, what is the chance of bag? Initially, the chance of bag was, it is H3, means 50-50, because prior was 40%. Prior probability was, so if we will say that 40% are the chances that the bag is 50-50. But when we take some observation, let me take just one. On this slide, we have taken few n pieces of candy, but let me take just one. So, as I take one observation, so I took one candy out of the bag and I see that it is lime candy. So the first candy is found to be lime. So what happened now? The probability of H1 was 10%, 0.1. But what happened now after doing one observation? When I got one lime candy, okay, now it is confirmed that it is not H1. H1 means all cherries. Okay, so this probability, which was 0.1 initially, prior probability of H1 was 10%, 0.1, now it has become 0. Okay, so that is our what? That is our posterior probability. Okay, now we can do reverse also. When we have to calculate it, we need likelihood. Now, how to find likelihood? So, likelihood can be found like this. See, I am given a bag. Let me say H1 is given. So, what is the probability of lime when H1 is given? That is 0, because H1 bag is having only cherries. What is the probability of cherry? That is 1. Same way, when I take H3, if my bag is H3, now what is the chance of being lime? What is the chance? What is the probability of observing lime? That is half. Cherry is also half. Okay, because we know the hypothesis, how the hypotheses are designed. What is the hypothesis? How the bag has been packed. according to H3, the bag has been packed such that half our candies are limes and half candies are cherries. Okay, so now the point is what type of predictions we can do here. Okay, so we have taken one example. What kind of bag is it? Okay, so let us try to understand this with our Bayesian learning. We are having prior probabilities, these. Then we are talking about posteriors. These will help us to find out what the bag is. So when I took the first candy, it is found to be lime. So it is confirmed that now it is not red one. Okay. When I took the second candy, now after taking the second candy, what I got? After taking the second candy, what happened? It is again lime. Okay. So it will affect the things. Which things? This has become 0 only after getting the first candy. But when we are getting 2 candies lime in sequence, one after one, so what are the chances? The probability of this has also reduced. What is this? In this, 3/4 are cherries and only 1/4 are limes. It means limes are only 1/4. So the chance of drawing the initially two lime candies should be comparatively low. So if we see this, the scenario, these were the initial probabilities for H1, H2, H3, H4 and H5. All are shown by different colors. Okay. If we see the probability of H3, what was the probability? What was H3? H3 was 50-50. Okay. So if I see this probability, it is 50-50 when I see the first lime candy. So it remains the same. The probability remains the same because when it is 50-50, what does it mean? It means one cherry has observed as lime. Definitely other will be, because half is the probability. The second should be cherry. But when again it is observed as lime, so this probability has decreased. This is posterior probability. Because if it was a H3 type of bag, then it should be 50-50, means we observe if 2 candies, one should be cherry, another should be lime. If I observe 4 candies, 2 should be cherry, 2 should be lime. That is the likelihood. Okay, but it has not happened. So posterior probability has changed. And if we see this one, H1 was total cherry. So it was initially 10%, but when first lime came, it subsequently becomes 0 because there is no chance of now of first one. Now if we observe these two means H4 and this one is H5. Okay, first line comes, both increased. Second line comes, both increased. But when third line comes, then the probability that 75% are lime also got increased, also got decreased. Why? Because when we are observing candies and we are saying that 1/4 are cherries, then some cherry should also come. But if we subsequently see this example, all are limes. Okay, so what happens? After doing 2 observation, 4 observation and so on, all the probabilities got decreased. Which posterior probability is high? That is H5, that the bag is carrying all the limes. So this way we do calculate the posterior probability. And same way I talked about if a hypothesis is given, we can find out the likelihood. So this is used to do the Bayesian learning. In this we have taken the prediction. When we have next candy is lime, what is the probability? Next candy is lime when we are given these observation. So next lime, the probability is going on increasing and increasing. Why? Because we are getting limes one by one. So we are getting the chance of that. Initially it was half. It could be cherry, it could be lime. But when it comes lime, after lime, it is going on increasing. Why? It is approaching 1. Why? Because the bag is, the probability that the bag is H5 has increased. So the next candy is lying, that probability has increased here. So this is our Bayesian learning concept. Now the point is, because we are calculating the weighted average, so the calculations are impractical in our this Bayesian learning. Okay, so we do an approximation with help of map hypothesis. So on this particular slide, we are talking about map learning. What is map learning? Maximum a posterior. In this, what we will do, we will make the prediction with the most probable hypothesis. When we do it, when summing over the total hypothesis space is very, very complex. It is intractable. In that case, what we do, we find out all the posterior probabilities and we take that hypothesis which is having the maximum posterior probability, as we have seen on our last to last one. This is having the maximum posterior, so we will assume it is H5. MDL. Now, if we see in this calculation, we are having the probability of D when HI is there into probability of HI. So actually, when we are finding the maximum probability for this, maximum posterior, we are doing the calculation for this because it is equal to this. So when we know that this is equal to this and we have to maximize this, then what we can do, we can convert this multiplication problem to addition problem to reduce the complexity. So what we can do, equivalently, we will minimize this. What we will do, we will apply log on both the sides. When you will apply log of this, so when I take log of this, it will be converted to this. Now we do not have multiplication here. The operator has changed. This is called MDL. Why we call it MDL? Because we can interpret this as choosing HI to minimize the number of bits that are required to encode the hypothesis HI. We are talking now about the number of bits that are required to hypothesis. That's why we are saying we may minimize it. That's why we have multiplied with minus. The optimization problem, maximization problem, we have converted to minimization. And it is now MDL. And the data D under that hypothesis. Okay. Okay, so the principle of minimizing code length is called minimum description length or MDL principle. So what we have done, we have taken log of that and we have converted map to MDL. This is our minimizing code length, minimum description length, MDL principle. Now one more thing is, if we are having all the prior same, see what we are doing here, we are multiplying with prior probability because the prior probabilities are different. If we consider our cherry example, in one it was 10% and 0.1 and one probability was 0.4. So the probability was very different. All the priors were different. But if we have same priors, and another thing is, when we are having very large data set, then prior becomes irrelevant. That doesn't have much effect on the calculation. Okay, in that it is enough to maximize only the likelihood. Then we take the maximum likelihood hypothesis, that is HML. So if in map we are having uniform prior, then we say it is ML, maximum likelihood. Okay, so we can avoid that. We can avoid that multiplication with PHI. When it will be taken? When our priors are same or irrelevant. When there is no reason to prefer one hypothesis on over another a priori. ML is the standard statistical learning method. It gets the best fit to the data. It is very successful. Now we'll talk about one more concept in this, that is learning with data. Now we are given data. We were talking about data. Now we are saying that we are learning with data. We are given data. So how do we learn when we are given data? We will discuss that 2-3 points here. We introduce parametric probability model with parameter theta. We do not know what is our hypothesis. Okay, so let us assume that the hypothesis is parameter is with these parameters theta. For example, we said there H1. So what was one parameter saying? That all are cherries. But now we are not aware of any which parameters are used. So simply we will say we are having parameterized hypothesis, that is H theta. It may be single scalar value or it may be many components. So using our data, we will predict the parameter theta. Theta will be predicted based on the data. So let us understand it with an example. Let us say we are having a bag of candies where limes and cherries are there, but we do not know it is 100% cherry, 100% lime. Means we do not know the proportion. Okay, so there is some proportion. Some are cherries, some are limes. But what is the proportion of cherries and limes, that we do not know. So this we have to learn. So what we will do? We will have a hypothesis parameterized by the probability theta of cherry. So let me consider that my parameter theta is my parameter is theta, and theta is the probability of cherry. Okay. Now I am given this probability of cherry, so my parameter is theta. Okay, so when I know that this is the chance of cherry, okay, so what will be my likelihood? It will be naturally considered as product of probabilities of my observation. So let me consider I have taken few observation. I took one candy and that is cherry. So I will take theta. Theta is the probability. Now I took another one that is also cherry. So into theta. I took another one that is lime. So 1 minus theta. When theta is a probability of cherry, then 1 minus theta is probability of lime. Okay, and so on. Now let me consider C number of kinds are candies are cherry and L are lime. So theta into theta C times into 1 minus theta into 1 minus theta L times. So this is my likelihood. Now I have to find theta such that it is maximizing the likelihood. Okay, so I'll find H theta which maximizes this. This is my expression. So what is the point here? We will make the expression. We will make the expression of likelihood. Okay, by taking the observation. So the same value can be obtained by maximizing the log likelihood. So we took here log likelihood. So this is my likelihood. I took log of this. So it will be log of P theta when log of P probability when observation is D and given the hypothesis H theta. Okay, and this is equal to this. So when I took the log, it will become C log theta plus this. Now I have to find theta such that it gives us maximum value. So how do we find the maximum value? This expression has come after taking a log, but now to find maximum we'll take derivative of this. When we will take derivative of this, it will be something like dl upon d theta is equal to c upon log theta. Derivative is 1 by theta plus L 1 minus theta minus L, because 1 minus theta derivative is minus L. So when we will solve it by putting it as 0 to get the maximum value, we'll get this expression. So we have learned theta here. What is theta? C upon C plus L. So this way we do the learning with our given data. So in this particular lecture, we talked about statistical learning. In particular, we have discussed Bayesian learning. Then we have discussed MAP, that is maximum a posterior, a minimum description length and maximum likelihood. And finally, we did one example for learning with complete data. Thank you. Jai Hind.